Hi, everyone. If you want to opportunities, if you want to use what we're doing for your research. So it'll be the story of this paper, error mitigation for partially error-corrected quantum computers, which I did with my PhD student, Ben, who's here as well. Quantum computers are getting pretty good. So this is a list of what's on the screen. It's more difficult. Thank you. Great. So quantum computers are getting pretty good. This is a table from a review paper that I did. At the time of writing it, it was up to date. Now there's been a few more. By the time it makes it through peer review, the table will probably be double the size. But you can see, from the first quantum advantage experiment in 2019, that was a random circuit sampling experiment by Google. There's been a lot more, mostly in these specialized problems, random circuit sampling, RCS, also Gaussian boson sampling, GBS, and some quantum simulation problems. We're pretty much right at the edge, and it's a moving boundary of what's advantageous that you can do on a quantum computer. Question?
Yeah, I've got a dumb question.
Please.
What do you mean by a quantum advantage in this case?
Great, thank you. So I should define. So quantum advantage means some well-defined computational task that you could do on a quantum computer faster than you can do on a classical computer. So, random circuit sampling is a very natural one for a quantum computer to do. It's not a problem that, from the start you might think has any use, but it's a well-defined computational task that you could do. And based on our current understanding of how to classically simulate quantum circuits, that what you can do on a quantum computer is better than what you can do on a classical computer. So here's a list of experiments. Like I mentioned, there's been a few more, but it's really encouraging, I think, to see. And if you think about the full history, classical computers have been around for a very long time. Quantum computers are much more recent, relatively speaking. And they're already doing some things that we can't even do. It's a limited set of things, but still interesting nonetheless. Of course, the natural problems are like simulating quantum systems. This is sort of just the obvious one that quantum computers do really well. In addition, there's a lot of progress in error correction. So here's a table from the same review paper about experiments, a brief history of quantum error correction experiments. And, in this table, there's a lot here, but, you could see numbers of qubits, like less than 10 for like a long time. And, now we're getting into the hundreds, 200s of qubits being used for error correction. And there's still, arguments of if we're beyond, break even, meaning like, better with error correction than without error correction. So that's not in every experiment, but that's in some experiments. So we're kind of right at this boundary of where these things are starting to get good enough to do things that are scientifically interesting on. Now, I don't think, personally, I would love to have your opinion on this and, audience poll or just poll of the experts. I don't think that we're going to wake up, one Tuesday morning and suddenly everything's going to be fault tolerant. It's going to be a transitionary period. So on this scale, which is how I like to think about it, as far as I know, this was first proposed by Dave Bacon, who's at Google, and then it was further sort of proposed by John Preskill. Just in terms of the number of quantum operations that you can do. So that's QOPs, quantum operation. If you do 1,000, that's a kiloQOP quantum computer. Preskill recently put out a paper about megaQOP quantum computers, so that would be 1,000,000, and so on and so forth. We're somewhere between here, like we're kind of here. And is there going to be a gap to doing, actually useful computations on a full fault-tolerant quantum computer? And so there's kind of a big hole in our understanding of, what do we do in this era? What can we actually use these sort of intermediate quantum computers for? And I like to think of this as quantum computers that are going to start having a few logical qubits. or a few better than physical qubits at least, but as well as a mix of noisy qubits that you can use in your computation. So there's a list of interesting questions in here. The first obvious one is, can you optimize or tailor any algorithm specifically to this hardware? As far as we know now, the only way you're going to do any quantum algorithm that's useful is to really think about the hardware, including the connectivity of the qubits, the operations that you have, so on and so forth. So in this setting where you have some good qubits, better than physical, some logical qubits, and a bunch of noisy qubits, what algorithms can you do on these types of devices? This is a very open question. Another one is just maybe more practical if you want to think about the software stack for how to actually run these quantum computers. How do I pick which qubits are going to be the logical ones? How do I entangle them with the noisy physical ones? Does that change throughout the course of the computation? And how do you do this optimally in the software that's controlling the computer? It's very, very open, very interesting questions. And more of the theory in terms of the computational complexity, does this fundamentally change the model of computing that we have? If we don't have a fully fault-tolerant quantum computer, but some of the qubits are noisy, does that change the complexity class of any of the algorithms that we know, or can we discover any new algorithms or sort of that sit in these new complexity classes? So these are all interesting. I'm going to talk about the last one, which is error mitigation. So even though we'll still have some good, probably better than physical qubits, it still seems very likely that we'll have a lot of noisy ones. And therefore, you still need to do something about these noisy ones in order to have a result of your quantum computation that's worthwhile. So that's what I'm going to focus on today. And the background is going to be on existing error mitigation technique known as probabilistic error cancellation. In the audience, besides Ben, has anyone come across this particular error mitigation technique? So let me explain. So what's the difference between error mitigation and error correction? So error correction means you're using additional noisy qubits to make a better qubit. And that is, as far as we know, scalable, although the overhead might be a little high in terms of how good you need the qubits to be and how many stabilizers you need to measure, so on and so forth. So scalable, but higher overhead. Error mitigation is the sort of inverse of that. It's designed to be low overhead, something that we can do now on a quantum computer to make the results a little bit better, but maybe not so scalable. So as you try to increase the size of the circuit, either the number of qubits or the number of operations, it's not going to scale as nicely as far as we know. But that's one of the problems that we're going to sort of attack in this paper. So let me explain to you how probabilistic error cancellation goes. We're going to think about the operations that I can do on a quantum computer, and I'm going to label these as a set of O alpha. So what does this mean? Like on IBM, I can do a C naught operation. Usually, sometimes it's a CZ operation, but that's the 2-qubit operation that I can do. And then I can do whatever single qubit unitary that I want. Okay. So let me just say whatever operations I can do are the set O alpha. And these aren't going to be perfect on the device, is the important thing. So if they were perfect, I could just do my algorithm and I wouldn't have to worry about it. But they're going to be noisy. And so I'm going to use O instead of U. So these are not unitary channels, they're general channels. And sticking with the PEC literature, I'll use the notation O for that. Some quantum operation, some channel. What I'm going to assume is that this forms a basis for the unitaries that I want to do. Okay. This is like the key of probabilistic error cancellation. It all just follows from this. So, you can even probably imagine what I'm going to do next. So I don't want to do a channel. I want to do the unitary that I want to do. And by assumption that this is a basis, I'm just going to write a single unitary in this basis. So maybe it takes, maybe there's capital M of them, and I can find some coefficients such that this is true, just by assumption that it's a basis. Now you might ask, under what assumptions does this form a basis? And there's some discussion about this. You can show it based on the model of noise that you're assuming, but it's not a totally unreasonable assumption to assume that this forms a basis. Yes.
What is mu, or is it n?
Capital M would be the number of operators in this set. So on a like IBM, this would be like, you know, two, a C naught and any single qubit unitary that I want to do. Or maybe it's like, you know, in a discrete set, Hadamard, phase T, and C naught. Yep. Yes.
So since you're dealing with unitary operators, are these O's here just the generators of the unitary group, or?
Good question. No, in this case, they're just the operations that the computer can implement. So you know, imagine I asked the computer to do a C naught. They're pretty good, as I showed in these tables. Like it's going to do a C naught like 99.99% of the time, maybe 3 nines, but you know that's pushing it. So but it's not perfect. So it's close to a unitary, but in general it's a channel. It's there's going to be some noise in the process. Yeah. Good questions. So all we're going to do in probabilistic error cancellation is now we're going to do this for every unitary in the circuit. What is a quantum circuit? It's a collection of unitaries, a product of unitaries. Let's say there's capital L of them. So I have L unitaries that I want to run in the circuit, and it's just repeating this equation L times. So the notation kind of sucks because you have to use subscripts, but you know, this is capital L, this is capital L, and then this repeats for every term. And then all we're going to do is just expand this. So alpha going from 1 to capital M again, C alpha, this is the first one now. O alpha, this is the first one. Okay, I didn't do anything as I used the basis. I assumed it was a basis. I expanded the unitaries, and then I just took my circuit and I did that for every one of the unitaries in my circuit. So you can very clearly see that there are M to the L terms in the summation, right? M to the L terms. And so to evaluate this exactly is going to scale very poorly, right? It's probably the worst scaling that you can have. So this is usually the defining feature of error mitigation. This is nice compared to other error mitigation techniques because it's actually an unbiased estimator. The more terms I evaluate, the better this is going to get. And I know that in principle, if I evaluate all of them, I'll actually get the correct answer. You know, and that's assuming I characterize the channels perfectly. But that's not too bad of an assumption. You know, maybe that's okay. So we can't evaluate this exactly. We're going to have to sample from it. So that's the probabilistic parts of the error cancellation. So we can write this generally as, let me just do it as a sum over vector alpha now, C alpha, O alpha. So the vector alpha is just the collection of all these different alpha coefficients. And then the O alpha is not a single operator, but it's a circuit. So each one of these corresponds to a different circuit that you would run. And so what they do in probabilistic error cancellation is something you might be all familiar with in other contexts. I'm going to pull this out as the following. So still sum over alpha, vector alpha, a probability distribution, P alpha, a sign, sigma alpha, and then still the collection of operators, O alpha themselves. Have you seen this before? It's a very common thing. So what's this gamma? This is going to be known as the negativity. It's the sum of all the sizes of the coefficients, C alpha. The sigma, like I said, is just the sign. Sigma is the sign of O alpha. And then the P alpha is just the normalized coefficients. So that gives us the probability distribution that we can sample from. Common technique, right?
It's a sign of C alpha, you mean?
Sign of C alpha, thank you. Okay, so if I want to evaluate an expectation value, you know, as we usually frame error mitigation, I can sample from this coefficient distribution piece of alpha, and then that gives me a particular circuit O alpha to run, which I run, and then I look at what its sign is, and I sort of add that to my total estimate. So like I said, this is an unbiased estimator. So the bias of this is 0. The variance will go by Let me define it in the following way, so I more clearly highlight the problem. Let me say that lowercase gamma is the negativity for each single unitary, so that capital gamma is the product of all of these. And in the worst one, we can take it, we could take it in the worst case to be the largest such gamma. So that means that this gamma really goes like gamma to the L, right? Just the product of L of them. And then if I want to get the variance of this, the variance of this expression will go by that squared. So it'll go by gamma to the 2L. So this is the biggest bottleneck or barrier to doing probabilistic error cancellation. But that's all the technique is. It's just really contained all in this one slide. So many have tried to sort of address this problem. So to reduce this overhead gamma of PEC, might be a little bit small, but I can zoom in. So here's 3 examples of this. So here's one paper by some of my collaborators, now at the Unitary Foundation, where they propose composing the PEC technique with a different technique, which would allow you to reduce the sampling cost. Okay. Another paper did this, where they presented an algorithm, an optimization algorithm that just tried to minimize find the best such coefficients to minimize this negativity. So that's one approach you could take to doing this. And a third one is actually in this last paper they propose grouping operators and reducing the number capital L and therefore reducing the overall negativity based on this. So I just want to emphasize that this is a problem that people have thought about, and we're going to also think about it, but in a slightly different way. So the way that I'm going to think about it is the following. What if we could evaluate all the terms in one go, meaning one run of the quantum computer? So I'm not sampling and then evaluating one O alpha anymore. Maybe I could do a sum of 2 O alphas with the coefficients, or 3 or more. So I want to imagine, what's going to enable me to do all the terms in one go, or maybe not all the terms, maybe just one, more terms than one, like we're doing in the conventional PEC. So let me write down an example of this. An example would be, let's just consider a single unitary circuit. So C1, O1 plus C2, O2, and I'll go up to 4. This will be like my guiding example to help you understand what's going on in the paper. So the traditional approach, as I wrote it down, would be, I see a question on the screen. How do we make sure C alphas are real? Oh, great question. That would be an assumption as well. And it's something that I thought about, but basically you just assume that this is true. And again, under some reasonable noise models, it would be, but in the general case, it's not going to be. Another thing that you could do, because when you implement the O alphas, those are unitaries, you can think about absorbing some of the coefficients into that unitary. And so if there's an imaginary parts, maybe you group that with the unitary, which might be okay. And then that makes the coefficients real. But let me just, it's a great question. Let me just say I'm going to assume the coefficients are real. So here's an example with 4 terms. What we would do before is I would run 4 circuits. So start in the 0 state as we usually do whatever the operator, the channel corresponding to O1 is. And then I would add this together for all of them. So C2 times this other circuit, and there would be 4 circuit evaluations here. Now, what I'm going to propose is that we try to do this in fewer than 4 separate circuit runs, and that's going to reduce the overhead of PEC. So as opposed to doing this, what I want to do instead, O4 and then measure, this symbol at the end, I'm just meaning measure in some basis to compute the expectation value that you care about. It doesn't matter too much for us. So what I want to see instead is that let's take this and let's do instead a single circuit where I want to think about doing the sum of all of these in one. So C1, O1 plus C4, O4, and then I can measure in whatever basis. So the advantage of this would be that we reduce the negativity in PEC. how do we do that? Because I don't have to sample anymore. It would just be one circuit. Or maybe if I do, some terms in one circuit, I have to sample less. So that's going to be the negativity reduction that we would get in PEC. The con is that, as you might imagine, the complexity of the circuit for doing this increases. So it's not just a single O1 that you can do natively on the device anymore. It's a linear combination of them. So the first thing we have to think about is how to do a linear combination of these channels with O1 through O4 in this example. And this has already been sort of thought about. A similar setting has been thought about, I should say. So not exactly the linear combination of channels, but some of the folks doing quantum computing in the audience will certainly have heard of the linear combination of unitaries. This is something that we use sort of as a primitive to do many quantum algorithms. So instead of doing the product of unitaries, which a quantum computer naturally does, I want to do, for example, the sum of two unitaries. And there's a very simple circuit construction for doing this, which I actually want to write down so that you understand it and can maybe take something away. So, by the way, if you zoned out, that was a good time to zone back in. You can take away how to do the linear combination of unitaries. So it just looks like this. I'm going to do have an ancilla qubit, which I start in the plus state, that is Hadamard applied to the 0 state. And then whatever state psi that I'm in, this is what I want to apply the U1 plus U2 to. Okay, so whatever state psi it is, all I have to do is I'm going to do a controlled U1 operator, and then another controlled U2 operator. But the notation here is that a closed control, this is the closed control, is controlled on the 0 states. So if this ancilla qubit is in the 0 states, then you apply the operator U1. And the open control, this one, is controlled on the 1 states. So if this ancilla qubit is in the 1 states, then apply the operator U2 to the other register containing psi. Then I'm going to do another Hadamard, and then I'm just going to measure in the computational basis this time. And so you can very easily analyze how this works. Let's just do it quickly if you haven't seen it before. So the initial state 0 psi, when you do the Hadamard, will give you 0 psi plus 1 psi. Okay, definition of the Hadamard gate. And then I'm going to do the controlled unitary operators. So on the 0 states, that's the U2. So 0 U2 psi plus 1 U1 psi. So I'm at this point in the circuit now. I've just applied the Hadamard and the two controlled operations. So you can kind of see that we're getting something close to what we want. There's a sum of U1s and U2s, but I can't quite group the terms yet because the ancilla qubit is in different states for the two terms, the 0 state and the 1 state. So that's what the last Hadamard gate does. What you end up getting is in the 0 states, you'll have U1 plus U2 applied to the state psi. And then you'll have some other terms which you could work out, which aren't interesting for us. What this tells us is that if I measure this ancilla qubit to be in the state 0, I would collapse the wave function, and then I know I would have applied U1 plus U2 on the state side. Okay. So this is an easy way that you could do the linear combination of unitaries in a channel. You can imagine how you might generalize this. So here, and by the way, I'm omitting coefficients like 1 over root 2. Hadamard gives you equal coefficients, but you can imagine if there's some other coefficients that you would want to prepare. Instead of the Hadamard gate, you would just prepare, do some operation which prepares those coefficients. Sometimes that's called the preparation gate. In our paper, we're just going to denote it as V. So it's some unitary operation which maps the 0 state to the coefficient distribution you want to prepare. And you do the sequence of controlled unitaries and invert the preparation and then measure. So that's linear combination of unitaries. In our case, I don't have unitaries, I have channels. These O's are not unitaries or channels, so I have to think about how can I do linear combinations of channels. Well, if you think about it for a moment, then you'll realize that the linear combination of a channel is not a channel in general. So I'll write that as LCC is not a channel. And just one example to show that. So let's consider the channel E alpha acting on a state rho to give us the outer products of alpha. And for example, for a single qubit state, this would be E0 of a single qubit density matrix goes to the 0 state, and E1 of a single qubit density matrix goes to the 1 state, okay? So you can see that if I consider a particular linear combination of these channels, E0 minus E1 is not completely positive, it's not even positive. So generally speaking, the linear combination of channels won't be a channel. Yes.
Right, I just realized there might be some people in the audience who don't know what a channel is. Ben covered it in the coffee discussion, but not everybody went to that.
Okay, so I'll say a little bit what a channel is. So in the remaining slide, but just to define it in a sentence, it's a completely positive trace preserving map, CPTP map. So there's two conditions, completely positive and then trace preserving. Trace preserving is easy. It means the trace of the channel is equal to 1. That just means it maps, density matrices to density matrices. And then the completely positive, just think about as positive. I don't want to get negative eigenvalues. So that's why I say this is clearly not negative. This is going to have a negative eigenvalue, -1. Okay. Completely positive is a slightly stronger condition than positive that we need in quantum information. If you're curious about what that is, you can ask me after. But okay, so you might be able to see already that how to fix this. Let's not consider a general linear combination, but let's consider a convex combination. So convex combination of channels, and I get to say CCC. So convex combination of channels will actually always be a channel. And so by this, I just mean let's consider for a collection of channels I, weighted combination PI times the channel EI, where this is a convex combination, meaning the PIs are non-negative and they sum to 1. So that will give you the trace preserving operation. If you take the trace of this, you'll still get a trace of 1 by virtue of the convex combination, the sum of the PIs is 1. And then it's going to be positive because each channel is positive and the PIs are also non-negative. And furthermore, it's going to be completely positive as well. So this is something that we can generally do. As I'll say at the end, there may be particular cases where we can do a linear combination of channels, and that might be interesting to consider. But in general, the convex combination will always be a channel, and so I can think about a procedure to do that. The last ingredient that we need is the following fact that, well, I like to say is the church of the larger Hilbert space. So this says that every channel is actually a unitary on a larger space. Okay, have you seen this equation before, or maybe this reasoning? So, no quantum system is perfectly isolated. It's always going to interact with its environment to some extent. We still assert that Schrodinger's equation is true on the full system plus environment. So the full system plus environment is going to evolve unitarily. But the thing is, we don't have access to the environment, so we can't control all those degrees of freedom. So when we ignore those, or when we trace those out, we do a partial trace over the environment, then that's going to give us the channel that we have. So, but you could also think about this the other way, that, because when I do this circuit for convex combinations of channels, I'm going to need to be able to implement a channel. So I can just think about that as a unitary acting on the system that I care about, plus some environment, which will be some ancilla qubits for us on the quantum computer. How do you actually do this? It's a textbook thing. So I took a screenshot of the textbook to show it to you. So this is box 8.1 in Nielsen and Chuang's Quantum Computation, Quantum Information. It's a standard way to, given a channel, collection of operators E sub k that I want to implement, to find a unitary U, which once I trace out the environment, the ancilla qubits, implements that channel. Okay. There's other constructions for this as well. In general, this is a dilation of the channel, meaning making it unitary. So we can now put these pieces together and do something that's similar to a linear combination of unitaries, but I know that I can't do the linear combination generally speaking. Also, I have to do a convex combination, and I don't want just unitaries, I want channels. So what I'll have to do is, here's the system that I care about. And you see the structure, it looks similar to the linear combination of unitaries, right? I just need another register of ancilla qubits that's just gonna play the role of our environment, that once I trace these out, it's going to implement the channel that I care about, and we've used subscripts to indicate those. These are the unitary dilations of the channel. Question?
Sorry, I have a question about the environment. Do you have to have some model of what the environment is to do the trace, or how does that work?
Great question. And to actually evaluate the trace, you would need a basis for the environment.
Right.
Without loss of generality, you can assume that the system and the environment start out in a separable state. And also that, yeah, there exists some basis for the environment. So yes, you're able to do this. So here's a new circuit that we introduced in this paper that was worked out very nicely by Ben. To do the convex combination of channels. Now, we expect that this is going to have general applications in a very similar way that the linear combination of unitaries does. And I'll mention an additional application at the end to just, simulating quantum systems. But maybe you might start to think already, and I would be curious to discuss how might you use this construction in your work, your research, if you want to simulate open systems, for example, which is the application that I'll mention. But before that, let me jump back to the application of error mitigation, which is how we framed this work and how I set up the talk. So let's see how this would go. Here is the original PEC, where we're sampling every term independently, and for each term, I'm going to run a separate circuit. So this, in our example, just to remind you, was the C1, start in the 0 states, apply O1, measure, plus so on. Where do we go? I'll go up to 4. We went up to 4. So this would be the O4. And then okay, that's the example that we had for this general equation. So, and then we wanted to do something that was the linear combination of channels, just to remind you. So maybe it takes more qubits, so I'll indicate that with the slash. So this was the C1 O1 plus C4, I guess, O4. And then I measure. And we weren't able to do the linear combination, but really that's not too bad. I can just split this into positive terms and negative terms. So let me pull out all the positive coefficients here. And I'll pull out all the negative coefficients here. And let's imagine, just for the sake of writing, that C1 and C2 are the positive ones. So C1 O1 plus C2 O2. I can still normalize, that's fine. And they're all positive. So once I normalize, this will be a convex combination of channels. And we just showed you the circuit construction to actually do that. So I can do all the positive coefficients in one circuit. And I can also do all the negative coefficients in the other circuit. Once I evaluate it, I just have to negate it, so multiply by -1. So C3 O3 plus C4 O4. Okay. What would the circuit be for doing this? It's the same one that I just showed you. Similar to the linear combination of unitaries, but not exactly it. The state preparation V, I would do a controlled O1 on whatever state row that I want to apply it to, and then an open controlled, anti-controlled O2. And then I didn't mention, but one nice feature of this circuit is that we actually don't have to measure the ancilla qubit at the end. What we're actually doing is tracing it out. So tracing it out, I ignore this qubit, and then I know that this state after this is the linear combination of the channels that I wanted to implement, and then I can measure whatever expectation value I would want to do. This circuit would be the exact same, except it would just be a different preparation unitary, as well as I'm controlling O3 and O4 here instead of O1 and O2. Okay. So let me mention that explicitly on the circuit construction. You can imagine in the linear combination of unitaries, there's some probability of measuring the ancilla qubit in the state 0. And so if it doesn't succeed, you would have to just rerun the protocol again until it succeeds. There's ways that you can boost this probability, but that's going to add overhead as well. So this is not a deterministic procedure. This is a probabilistic procedure. And if it fails, if I measure the ancilla in the 1 state, then I just stop the computation. I have to rerun it and until I get to 0 state. So a nice feature of the linear convex combination of channel circuit is that this is totally deterministic. So there's no stopping and restarting that we have to do. This is a deterministic procedure. It succeeds with probability 1. So you'll notice a slight difference in this case now that I didn't insert the ancilla register that do the unitary dilations for the channel. The reason that is slightly subtle, but just think back to the application that we're doing. The application I'm considering here is quantum error mitigation, where by assumption, we posit that the unitaries themselves are not perfect, but they correspond to some channel which forms a basis for operators. So I don't need to dilate the channel that I want to implement. In a sense, the quantum computer is doing that for me. We wish it wouldn't, because then we wouldn't have this whole error mitigation mess. But the channel that we implement is, the unitary that we implement is going to exactly correspond to this channel. But we are controlling it now, and so that can change things slightly. So what we do, and where the mixed noisy and logical qubits come in, is that we're going to assume that these ancilla are noiseless. In other words, logical qubits. Okay, so that is the error mitigation for partially error-corrected quantum computers. I'm imagining I have a small number of qubits which are perfect or at least better than physical, and those would be the qubits that I use to prepare the coefficient distribution, and then these would be the noisy ones where I'm doing the error mitigation procedure for. Okay. So all I have to do is I just have to control those channels in order to implement this procedure, and then we're going to assume that these are noiseless. In other words, we're working on a computer with mixed noisy and logical qubits. Okay, so if you look in the paper, you'll see this equation, and this corresponds exactly to what I wrote down here. So the positive coefficients, those are the gamma plus. In our example, that would be this term that we evaluate. The negative coefficients would be here, corresponding to the other term. So the formal statement, this is the intuition, which, you know, to me is the purpose of talks that I like to give. And then, you know, if you're interested, you could read the paper more. But let me skip this and come back to it. To see the formal statement, if you look at the paper, it'll look like this. Provided a number, linear in K, let's just say it's K logical qubits, then I'm actually going to be able to sample a certain number of terms in the expression of probabilistic error cancellation. And it's going to decrease the negativity, the overall negativity, from gamma to the L to gamma to the L minus K. Okay, so this is the reduction that we're able to get in this procedure. And correspondingly, that reduces the variance from 2 to the L, gamma to the power 2 to the L, to again subtracting out K. The delta in the denominator is just the usual thing. It's the accuracy that you want the expectation value to be within. So here's another way, I mentioned a few others that people have tried to reduce the negativity of probabilistic error cancellation. Here's a way that you could do it, assuming you had access to some logical or better than physical qubits on your device. Now you could take this to an extreme, meaning let's take K to be equal to L. And if you see that, you see a interesting thing, which is that the negativity of PEC actually goes to 1. The overhead of PEC goes to 1. So that's nice, but you have to be careful because there's a bit of a balancing act. L, remember, is the number of operations in the circuit. Usually that's going to be more than the number of qubits in the circuits. Otherwise, it would not be too interesting of a circuit. So if you had that many logical qubits, well, then you might as well just run the logical version of the circuit that you want to run. And then so you don't need to do any error mitigation. So there is that sort of extreme that you can push it to, but again, it's a balancing act because if you had so many logical qubits, then you wouldn't need to mitigate errors in the first place. In any case, though, given a few logical qubits, we are able to use this to reduce the overall negativity of probabilistic error cancellation. Let me mention the last statement, which some of you might be more interested in. So that is the application of simulating open quantum systems. And we have one example of this in the paper. So in general, you can consider like a Lindblad equation to model Markovian dynamics. And the example that we considered was that of damped Rabi flopping in a two-level atom. And what we did was we took this sort of textbook example, we implemented it in our circuit, and then we implemented it in a state-of-the-art procedure for doing this from these references. And we are showing that we're able to do this with quite fewer resources. It's still in general open to be understood how much we can reduce this, but it's at least notable. And this is a very general construction that we have, for any convex combination of channels. And this is just one example showing that we can reduce the circuit complexity compared to other proposals for doing this. Now, in this setting, we're imagining a fault-tolerant quantum computer, right? Nothing is noisy here. I'm just saying, let's suppose I can do the circuit exactly as I want it to implement whatever open quantum systems evolution that I want to do. And these would be the operation counts that you have. So I'll leave you with some open questions. It would be very interesting to consider if we could do the same protocol, either exactly or approximately, with some noisy ancilla qubits. So relaxing this assumption that they have to be perfect. I strongly suspect that this is true, at least under certain error models. And you might be able to think up some error models on the ancilla in which the errors actually don't matter for the overall convex combination of channel circuit. And then so that we would be able to do this actually currently experimentally, which would be interesting. And in this case, you also sort of get around this balancing act that I mentioned, where you have to be sure the number of logical qubits is not too large. Because in that case, we would still have noisy ancilla. And maybe you could even tailor the noise such that you get it to be what you need it to in order to do this protocol. So if we did that, then we'd actually be able to experimentally demonstrate this and show experimentally we can do this to reduce the overhead of error mitigation, which would be very interesting. It would also be interesting to consider, although it's in general not possible. I wrote down an example of you where the linear combination of channels is not a channel. Certainly there are some where it's true. And so you might think about, can we construct a circuit for this case, linear combination of channels when it is possible? And then can we use that maybe to further reduce the PEC negativity? And then the last one, which I would love to discuss with some of you all, is what other open quantum systems might you want to simulate with this technique or maybe a similar technique? And then how much could we reduce the circuit complexity, the number of operations in the circuit, with our technique compared to other state-of-the-art? So I think I'm about at time. So thank you for your attention.
Are there any questions?
So Ryan, thanks very much. So I'm trying to connect this with my intuition about Monte Carlo sampling, right? And to what extent is this the standard approach that you started off with the probabilistic error cancellation? To what extent is this polynomial scaling, and to what extent is it exponential scaling if there's no sign problem? I don't have a good sense of that.
I guess if there's no, so I don't understand it fully. I guess if there's no sign problem, then it would be polynomial scaling.
Okay.
Now, the extent to which there is a sign problem, I think is also kind of open. There might be some discussion about this, but I think for most error models, like you're going to have a sign problem.
Yeah.
There might be some cases where you don't, and that could be interesting to look at.
Okay, because the analysis you had of the cost in terms of the negativity, I didn't see the sign enter that calculation, because to me that was the sign problem is is the whole thing. It's the whole game of how difficult it is.
I guess it would come in here.
Because you do the absolute value of gamma. Okay, so then the negativity. The small gamma, what was the definition of that?
This small gamma up here, would be similarly the sum over all the coefficients C alpha for this single unitary. And then the capital gamma is the product of all of those, which you get out when you do this expression.
Okay, yeah, so I guess it's captured, the sign problem's captured there.
Yeah.
Okay.
I should say there is some discussion, Dean, on like, not in the context of PNP, like in the context of simulating circuits where like they're mostly stabilizer circuits, but they have, sorry, mostly Clifford circuits, but have like, a few non-Clifford gates, like a few T gates, for example. There is some discussion about like which channels can be efficiently simulated using convex combinations of Clifford channels. And so I think there's kind of like, if you parameterize the space, there's kind of like a geometry of like which channels, there's like a convex hole within which the channels are easy and outside of it, they're hard. I could try to find the paper to email to you.
Thanks.
Yeah, thanks.
Yep.
Yeah, I have a very simple question about quantum supremacy to address the meaning of your talk. So you need a reference to establish quantum supremacy. You need to know a classical algorithm, how fast it goes, or in order to know if you are going faster or not. But this classical algorithm, for example, they could be implemented on a single CPU or on a huge machinery with, thousands of CPUs. So in order to establish quantum supremacy, do you need to fix the number of CPUs that are employed for the classical calculation?
It's a great question. So usually what people do is they fix them to be the best classical computer on Earth, meaning the best supercomputer, whatever it is at the current time. And it's never a proof. It's a belief, right? 'Cause, how could you rule out that there is no classical algorithm on any classical computer that could do this? So it's certainly a belief. It's a justified belief. What people do is they'll say, here are the best known algorithms that we have. We tried them, we estimated the resources, and this is what it would take. And then we did it in this amount of time on the quantum computer. Having said that, it is very much a moving target because classical algorithms are going to get better, classical computers are going to get better, and quantum computers are going to get better too. So the first experiments have been refuted. The estimate based on the best supercomputer and best algorithm at the time for the original random circuit sampling experiment by Google was like 10,000 years, or was famously what it was said. And then someone, just a few years later did it on a small GPU cluster in a matter of minutes, and then later on even faster than the quantum computer did it, which was a few seconds.
So in order to have a less time-dependent measure, wouldn't it be possible to establish this quantum supremacy per energy used using the machine? So of course you can always scale a classical computer, but then it costs a lot of energy. But if you rescale everything by energy, then you will see which one is really it costs less energy to get the same results.
Yeah, I think it's a great idea to think about per energy instead of per time. You can go down quite a philosophical rabbit hole with this, I think. Should we normalize by the amount of brain hours that have been spent thinking about the algorithms as well, so on and so forth. So it is tricky, but in a lot of ways, energy is a better metric than time. I would agree with you.
Any other questions? So I guess a quick follow-up on that is, are quantum computers even as optimal as current classical computers? Like in terms of technology, coefficient of useful action, is it, if you give like X amount of energy to it, do you get actually X amount?
Yeah,
Good.
it's a very good question. So here's a very limited set of problems. Random circuit sampling. It has been argued that you could use this for cryptographic purposes, and then it actually has been there's follow-up work about this, so, cryptography is, useful. Gaussian bosons, maybe there's others like this. I think everyone in the room would argue that quantum simulation is important and impactful. So, whether that's for designing a molecule, making up a drug, or, studying health, or studying a nucleus, So here it's very a limited problem set, but even within the space of, quantum simulation, that is, obviously very impactful.
Any more questions? John?
Yeah, so I'm not quite familiar, but could you give more examples on what kind of open quantum systems you might be at last? Because to me, the open quantum system is something which you have some relation with a continuum or some effects, right? So
Yeah, so that's actually something that we're still thinking about. What we did was a sort of textbook example of this, Robbie flopping. And there's certainly, others that we could think about, but it's kind of my question to you all. So I'll turn it back of, what other open quantum systems could we look at simulating with this technique? As I mentioned, the circuit structure is very general. So, if you take one thing away from this talk, I guess I would want you to think about the circuit structure for implementing a convex combination of channels, and there could be variants of this. But as it's written right now, you could do this to do quite a general set of things. And so what might we want to use this for?
Good. No questions on Zoom. Great. There's no more questions. Let's thank Ryan again. Since Ryan is a faculty at MSU, you can always contact him. I can send everyone his email address, Ben's email address, if you want to collaborate on anything. Thank you.